Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the first module of this course, that is the introduction module. And the idea behind this module is to give you a basic introduction to operating systems. So within this first module, currently we are on the first topic, that is computer hardware review. And in this topic, basically we want to review the concepts of computer hardware. As I said in the first video, that the operating system is a piece of software that is responsible for managing the computer hardware. Hence, in order to understand what is an operating system and what does it do, how does it function, it is very essential for us to have a good understanding of how the computer hardware works and what is the hardware interface that each of these hardware components exposes to the operating system. So what we are going to do now, so as I already said, there are three major hardware components. The first one is the CPU, the second is the memory, and then we have a set of IO devices. So now we are going to take each individual hardware component and study them in more detail. We are going to study the functionality of each piece of computer hardware, their internals, and what is the interface that each of these hardware components exposes to the layer of operating system. So we are going to start with the first and the most basic and important hardware component, that is the CPU. So let us start this video and look at CPU in more detail. So let us start the discussion with this very basic model of a computer. We have already seen this model in the first video. So what is this model trying to convey? Basically, it is trying to say that any computer, however complex it might be, is organized in this fashion. So there are three major components in this model. You can see the first one is the CPU or the processor. Then we have the memory, and then we have a set of IO devices, right? Here we have n IO devices. And all of these major components, hardware components, are connected by an interconnection system that is called bus. So this is how the computer system is organized. Now what we are going to do, we are going to take the CPU, the processor, and understand what it does. So in order to understand what does the CPU do, let us revisit this von Neumann model. So essentially, this model tries to convey how does the computer work. The previous model was a depiction of how the computer system is organized, what are the major components. But this model, the von Neumann model, it tries to depict how does the computer function and what is the functionality that each of the hardware component provides. So here we have the CPU. So basically it starts with the input devices. We as users of the computer, first of all, give some kind of input via this input devices. And this input is some kind of information that we want the computer to process for us. So after the computer has done some processing, it will produce some new data, some output data that we want, right? So we give our input via this input devices, and that input goes and sits into the memory. And as we already know, that the information in the memory, whatever information there is, it is of two types. The first one is the data. It is the data or information that the user has provided as input, and the user wants the computer to process this data. So this data can come in various format. For example, text input. Then apart from text, we can have images, we can have audio files, video files. All of these are different formats that can be associated with the input data, right? And now that we have data, we need a way to manipulate or process this data. And this is where we have instructions. So the second type of information that exists in the memory is the instructions. And these instructions are basically commands for the computer that tell it how the data has to be processed, right? And these instructions come in the form of a computer program. So a computer program is a set of instructions, and each of these instructions is basically saying how the data has to be manipulated or processed. So now we have the instructions and the data, they are present in the memory, right? And all of these comes as input from the user. Then what the CPU does, it basically fetches both the data that has to be processed and the instructions, and these instructions tell how the data has to be processed. So the CPU fetches both the instructions and data, and then executes these instructions one by one. So there will be some computer program having a set of instructions, and the CPU will basically execute these instructions one by one. And after executing each instruction, some processing keeps on happening, right? And at the end of at the end of the program, whatever data or the output has been generated, that is sent back to the memory, and this data is then sent to the output devices. And from the output devices, here is where the user can consume the data that has been generated by the CPU. So the flow goes like information comes from input devices by the user, via the user, and sits in the memory, and this information is either a data or an instruction. And what the CPU does, it has to process that data, so it fetches that data along with the instructions which tell it how to process that data. It executes these instructions one by one, and whatever output data has been generated after execution is then sent to the memory, which is then sent to output devices for the consumption of the user. So if you see closely, the core functionality of the CPU or the processor is to execute instructions. By executing instructions, it is able to manipulate data, right? So execution of instructions is the basic function of a CPU, and any modern CPU has the capability of executing millions and billions of instructions per second. So now we are going to look at what are the major components that are there in the CPU, which enables it to execute these instructions. So this is the CPU. Now let us look at what are the major components inside this. So as you can see, there are two major components inside the CPU. The first one is the registers, and the second one is the execution circuit. So basically, registers are a form of storage. They support transactions at very high speed. So when I say transaction, I mean reading and writing. So it is a kind of storage from which you can read and write at very high speeds, right? So as I said, CPU is capable of executing millions and billions of instructions per second, and in order to support this speed, this speed of execution, we need a type of storage which can read and write, which can support read and write at a very high rate, right? So compared with the memory that we saw, these registers have a higher speed than the memory. And then we have the execution circuit. So basically, if you see the CPU, it is a kind of electronic chip, and there are a lot of circuits on this chip. So if you separate out the registers, the storage part, then whatever remains after separating out the storage part comes under the execution circuit. I have used this execution circuit just as a placeholder to separate out all the circuitry that is apart from the storage. And this circuit is basically responsible for the core execution of the instructions, the processing, the manipulation of data. All that circuitry comes under the execution circuit. So now let us look at registers as well as execution circuit in some more detail. So now let us look at the registers. So there are two types of registers. The first one is the general purpose registers, and then we have the special purpose registers. So let us first talk about the general purpose registers. So as the name says, they are used for general use, right? So when the CPU is executing instructions, these instructions are basically manipulating some data, and these data are called operands. So first of all, these operands have to be fetched from memory, and where are they fetched? So they are fetched in the general purpose registers. So as part of executing an instruction, the operands are then first of all transferred from the memory to these general purpose registers. These registers are named sequentially. You can see from 0 to n. Just giving you an example, these names are sequential, right? And once the operands are present in these general purpose registers, then the CPU can go ahead and execute the instruction, right? And what the CPU will do, it will use these values in some way. Maybe it will combine the operands to produce a new result. In whatever way it uses, if a new result has been produced, right, that result will also be stored in the general purpose registers. So you can think of this as a scratch memory, where the CPU stores the operands and the results when the execution of the instructions is going on. So now let us talk about the special purpose registers. So as the name suggests, each of these registers has a special use, a special purpose. So here I have taken some examples. There are many special purpose registers. I have taken only a few. I have taken 4 examples. So let us now talk about these registers one by one. The first one, that is PC, is short form for program counter. So the program counter is a very important register. It stores the address of the current instruction that is being executed, right? So as I said, a program is a sequence of instructions, and the basic purpose of CPU is to execute these instructions, and these instructions have an address. So the instruction that is currently being executed, first of all, that has to be fetched, and that fetching requires an address, and that address will come from the program counter. So as the program execution proceeds, this program counter gets incremented or updated, and the CPU, how does it know which instruction it has to execute next, comes from this program counter. Then after program counter, let's talk about the instruction register or IR, right? So this instruction register is very similar to the program counter. It basically stores the current instruction. So the program counter stores the address of the current instruction, and instruction register stores the current instruction itself, right? So basically before executing any instruction, it has to be decoded. So remember that instructions and data are initially present in the memory. So these instructions will have to be fetched. So when that instruction which has to be executed is fetched, it is first stored in the instruction register. And when the instruction is in this register, the CPU then can decode what kind of instruction is this, what is the operation that has to be performed, what are the operands that are part of this instruction. So this is the placeholder for the instruction that has to be executed, right? Then we have the stack pointer. So stack pointer, basically stack, let's first understand stack. Stack is a region in memory that is used for the execution of functions. So we will study about stack in more detail when we talk about when we study operating systems in the next module. But a very basic idea, to give you a very basic idea. So a stack stores basically an object for every function that is part of the program. So if you see any program, it's a collection of functions. Whenever you are executing, you are inside some function, right? So what the stack does, for every function that has been called, an object is pushed onto the stack, and the stack pointer basically points to the top of the stack, and this basically gives an idea to the CPU in which function we are currently in, right? So this is how the stack pointer works. It stores the pointer to the top of the stack, and stack is a memory region that is used for the execution of functions, right? And then let's talk about the program status word. So program status word is basically a collection of different flags, right? A register has many different many bits, and each bit is used as a flag in this program status word. So as the name suggests, it kind of denotes the status of the program execution. So as your program is executing, the instructions are getting executed, the status changes. So let us talk about some flags to give you a basic idea. One of the flag that it has is the overflow flag. So when your instructions are getting executed, it basically, overflow flag indicates whether the result that was produced as part of execution of the previous instruction overflowed or not. So as you can see, the register is a limited form of storage, and sometimes the value that that has been produced can overflow the register. So this is one kind of status. Then there is a zero flag, basically whether the result that was produced was a zero value or not. Similarly, for a negative value, there is also a flag. And program status word can also store whether some error occurred or not, whether some exception has occurred while execution of instructions. So it's basically a place where you store different pieces of information in as a collection of flags in this program status word, and it can be used by the CPU to check and see if some condition has occurred, and depending if that condition has occurred, some special action has to be taken or not. So this was about the program status word. So these are some of the examples of special purpose registers that we just saw. Now let us talk about the execution circuit. So now let us talk about the execution circuit. So as I said, if you talk about the CPU, it's an electronic chip, and all the circuitry, if you take out the storage, the registers, all that circuitry that is left, I have clubbed that into the execution circuit. And within that circuit, there are several components or units. And here I have shown only few. One is the arithmetic and logic unit, and the other is control unit. So these are important units. And apart from these, there are several other units also. It's a very complex chip, but just to give you a basic idea what are the kind of components that you can expect in this execution circuit, I have taken two examples, right? So there is the storage, that is the registers, and there are these components or circuits. So let's talk about the ALU first. The ALU stands for arithmetic and logic unit, and as the name suggests, this unit is where the core arithmetic and logic operations are performed. So you see, the instructions that we have in our program, most of them are arithmetic and logic operations. So you're combining two values, two or some operands, right? You're combining some operands in some way. That way could be an arithmetic operation like addition, subtraction, division, multiplication, or it could be a logic operation like and, or, not, right? So a lot of operations in these instructions are arithmetic and logical. So this is the unit where that operations are performed, right? And it takes some operands and combines them in some way to produce a new result, right? So this was about the ALU. And then we have the control unit. So as the name says, the control unit is responsible for controlling the behavior of the entire CPU. So what it does, it basically decodes the instruction that is present in the instruction register. It figures out, okay, what is the operation that has to be performed, and based on that it sends out signals, control signals, which kind of orchestrates what is going to happen when, right? So it's like a nervous system, right? It sends out signals which control other parts of the CPU. So the control unit you can think as the nervous system of the CPU, which is responsible for sending control signals, which will be orchestrating what is going to happen when in the CPU. So this was about the control unit, right? So these are the two examples that I took. There are many more units and complex circuitry as part of the execution circuit. So this is how the CPU looks like. From our perspective, this is a basic view of the CPU. There is a storage, right? Storage have general purpose registers or special purpose registers. And then if you leave out the storage, whatever remains, whatever circuitry remains on the CPU chip, you can call it the execution circuit, which has many different components. And we talked about two of them, that is ALU and control unit, right? So now that we have a basic understanding of what the CPU does and what are the major components inside this CPU chip, we'll now understand how does it do its job, right? So let us now understand how does the CPU function. So as we already discussed, the basic job of the CPU is to execute instructions. And as we know, a modern CPU can execute millions and billions of instructions per second. Now, this execution of instructions happens by following something known as instruction execution cycle. So let us understand this instruction execution cycle to have a good understanding how does the CPU work, right? So this is the von Neumann model, and this is the CPU. We already discussed that there are two major components. First is the registers, and then we have the execution circuit. And the sole purpose of the CPU is to execute instructions, right? So the way these instructions are executed, it actually happens in a series of steps. Any single instruction is not executed in one full go, right? So it is done in a series of steps or stages. So and the number of steps and the exact steps can vary, but let's take a simple example and see how does it happen commonly, right? So here as you can see, I have taken 5 steps. So each instruction will be executed using these 5 steps. So let us understand what are these steps. So the first step is the fetch. So fetching is the stage where we fetch the instructions from the memory. So as you can see, both instructions as well as data are initially present in the memory. And as the CPU executes these instructions, it has to first bring these instructions into the registers, right? So this is the fetch stage. After the instruction has been brought into the registers, it will be present in the instruction register. We already talked about the instruction registers when we talked about special purpose registers, right? So the next step is the decode. In this step, whatever instruction is present in the instruction register, which has to be executed, the CPU will decode it. In decoding it, first of all, understand what is the operation that has to be performed. There are a wide variety of operations that the CPU can perform, right? First of all, it has to understand which specific operation is being requested in this particular instruction, and also what are the operands for these instructions. So decoding the operands as well as the operation happens in the decode stage. And then we come to the main step, that is the execute step. So whatever operation that was detected in the previous step will be performed in the execution stage. For example, if it is an arithmetic operation, let's say addition, then in this step the operands will be added to produce a result. So this is the execute step. And then finally the next step we have is the memory access. So there are two types of instructions, you can say. One that are involved in the execution. In execution, some operands will be manipulated or combined to produce a result, right? Some kind of operation is done in the CPU. And the second type, you can say, is memory access. So these are data movement instructions. So either you can bring the data from the memory to the registers, which is called a load, or you can store, basically move the data that is present in the registers to the memory, that is a store operation. So load and store operation basically move the data between the memory and the register. And if the current instruction is a load or a store operation, then in this step memory will be accessed, data will be transferred between the memory and the registers, right? The last step is the write back. So let's say it was an arithmetic operation and some new result was produced. So any instruction that produces a result, that result has to be written back into the registers. So as I said, in the general purpose registers, initially the operands are stored, and if the operands are combined to produce a new result, that is also stored in the general purpose registers. So this is the write back part. So you see there are a series of steps that are involved in the execution of an instruction, and any instruction that will be executed by the CPU will be done following this series of steps. And as I said, this series of steps, the number of steps and the exact nature of steps can vary upon the CPU. Different CPU will have different number of steps, but the core idea behind this instruction execution cycle is that an instruction will be executed in a series of steps, and once that instruction is done, the next instruction will be executed. So this cycle is followed. So let's say you have one instruction, the CPU followed all these steps, that instruction is done, then next instruction is started, and in this following this cycle again and again, the sequence of instructions is executed by the CPU. So all the instructions are executed by following this cycle that is known as instruction execution cycle. So now what we'll do, we'll take an example and understand how does this instruction execution cycle work in practice. So here, as you can see, we have an example program. So this is the memory, right? And in the memory we have an example program. So a program is basically instructions as well as the data. So this is a very simple hypothetical program which is doing nothing but adding two numbers, and these are the four instructions that are involved in that addition. So let's go over these instructions. So the first instruction is a load instruction. Load instruction will move the data from the memory to the register. What it is saying? It is saying move the data or load the data from memory location 100 to register R1. So here we have the 100th memory location and it is storing the value 20. This instruction is saying move this data to register R1. So in the general purpose registers, we have the register R1. So this 20 has to be moved here, right? Then the second instruction is similar. It is saying move the data at memory location 104, that is this 30, to register R2. So R2 is here. So basically, first of all, bring both the numbers that you want to add, first of all, into the general purpose register. So these are the operands for this addition, right? Then this instruction is saying addition. So it is saying whatever value is there in R1 and R2, add those two values and put the result in R1. So we have this addition instruction, we have the two operands, the result has to be put again in the R1, right? And then the final instruction, it is saying store the value, whatever was produced as part of addition, that is in R1, into the memory location 108. So R1 will contain the result of the addition that has to be stored in this 108th location. So this is a hypothetical program with some example instructions and data, and it is this program is starting from address 120. So you see the program counter stores the address of the first instruction. So now when we begin execution, we'll start execution from this instruction. So these four instructions make up the program. This is the data for the program. And let's now see how these instructions are executed by following the instruction execution cycle. So let us start the execution of the first instruction. So as you can see, the program counter is currently storing the value 120, which means our first instruction, that is the load instruction. So as we already know, the execution of any instruction will follow this execution cycle. So the first step in this cycle is to do the fetch. So when we do the fetch, this instruction that is pointed to by the program counter will be loaded into the instruction register. So let us do the fetch. So as you can see, this instruction has been loaded into the instruction register. And also one important thing, the program counter has been updated. It has been incremented to point to the next instruction, that is 124, right? So this is the next instruction that will be executed after the current one is finished. So this is the fetch step. Next is the decode step. In this step, basically the CPU or the control unit, you can say, it decodes the instruction. When it is decoding the instruction, it will figure out what is the operation that has to be performed. So in this current instruction, it figures out, okay, now I have to do a load. What is a load? Loading means moving some data from the memory to some register. So it also figures out what are the operands. So the first one is the 100th memory location. So this is the source location and the destination location is R1. So it figures out, okay, data has to be moved from 100 to R1. So the control unit will accordingly send out signals, right? So this is the decode step where we figure out the operation and the operands. The next step, that is the execute step, it won't happen in this instruction because this is a data movement operation. Here we are not doing any arithmetic or logic operation where operands need to be combined to produce a new value, right? So if you see, the addition operation is where execution is required. Here in the load and store, this step is not required, hence this step will be skipped and will go directly to memory access. Similarly, in addition instruction, memory access won't be required, only execute and write back will be required. So now in this memory access, what will happen? Here we will move the data from the source to the destination. So from 100th memory location, this 20 is moved to the register R1, right? So this memory access has been done. And finally, no write back is required because here we did not combine any two values to produce a new result. So no new result was produced, only data movement happened. So the important point is that there are certain instructions like data movement where execution and write back are not required and only memory access is done. So these two steps will be skipped. Whereas there are certain instructions where we combine two values in the execute step, and whatever new result has been produced, we write back that into the register file or the general purpose registers, right? So this is the load instruction. So again, write back step will be skipped, and this completes the execution of our first instruction. So after completing the first instruction, this cycle will be again followed for the second instruction. So let us go ahead and execute the second instruction following this instruction execution cycle. So as you can see, the program counter is currently pointing to 124, which is our second instruction. And this is a load instruction, which is very similar to the first instruction that we just performed. So the first step is to fetch this instruction. So as you can see, now the load instruction, the second load instruction, has been loaded into the instruction register, and again the program counter has been accordingly updated, that is 128, right? So this is the fetch step. The second step is the decode step. Here basically the CPU will figure out, okay, this is a load instruction and the source operand, source location, the first operand is memory location 104, and the destination location, the second operand, is the register R2. So it figures out, okay, this is a load operation where we have to move the data from 104th memory location, that is storing 30, to the register R2. Then again the execute step will be skipped, right? It's not any arithmetic operation, it's a data movement operation and will go directly to memory access. So the next step is the memory access. Here as you can see, the data dashboard that was present in memory location 104, that is 30, has been moved to register R2, right? So this memory access has been done. And finally, no write back is required because it's a data movement operation and we did not produce any new result. So this write back step will be skipped. And now as you can see, the second instruction has also been executed by following this cycle. And now let us execute the third instruction. So now let us execute the third instruction. So as you can see, currently the program counter stores the value 128, which means the third instruction, the addition instruction. So again, we'll follow this cycle. The first step is to do the fetch. And when we fetch the instruction, this addition instruction has been moved to the instruction register. So this completes the fetch step, and accordingly the program counter has now been updated to point to the fourth instruction, right? That is 132. After the fetching has been done, the next step is to decode. So in the decode step, basically the control unit figures out, okay, this is an addition instruction, and what are the two operands, that is R1 and R2. So these operands have to be fed to the arithmetic and logic unit because now we have to do an arithmetic operation, which is addition. and accordingly these operands, that is R1 and R2, which store the value 20 and 30, these values are read and they are made ready for the ALU, right? So this is the decode step where the control unit has figured out the operation as well as the operands. Now we'll do the execution. So the next step is to go ahead and add these two values. So the arithmetic and logic unit will combine 20 and 30, do the addition operation and produce the result, that is 50. So this is the core execution step. And then the next step, that is memory access, this is not required because this is not a data movement operation, right? So now this step will be skipped. And finally we'll go to the last step, that is write back. Since we produced a new value, that is 50, so after adding 20 and 30, a new value was produced, that is 50. This value has to be written back, and where it will be written? It will be written to register R1. So add R1, R2. Here it is saying add the values R1 and R2 and store whatever result has been produced back into R1. So now as you can see, R1 has the value of 50. So this completes the execution of our third instruction. So now let us execute the final instruction, that is the store instruction. So as you can see, the program counter is pointing to 132. That is our final instruction. So let's follow this cycle once again. So when the fetch step is done, so you can see this instruction, that is the store instruction, has been loaded into the instruction register and the program counter is incremented to point to the next location. So this is the fetch step. Our instruction has been loaded, right? Next, there is the decode step. So in this step, basically the control unit decodes the instruction. It figures out, okay, this is a store operation. And what are the operands for this instruction? There are two operands. The first is the, so this is a store operation. The source location for storing is the R1 register and the destination location is 108. So basically here we have to move whatever data is present in R1, that is 50, to the memory location 108, right? So the control unit figures out this store instruction and accordingly it generates the control and timing signals for other units. So the next step, that is the execute step. This step will be skipped because this is a data movement operation. Just like load, here we do not need to do any execution. We'll go directly to the memory access. So let us see the memory access. As you can see, when the memory is accessed, this value, that is 50, that was in register R1, has been stored into the memory location 108, right? So this is the memory access step. The store has been complete. And finally, the write back is not required. Just like in load, we only did the memory access. Execution and write back was skipped. So for the store instruction also, we'll skip the write back. So now you can see we have done all the 5 steps and this instruction has been executed. The value has been stored into the memory. So now all the instructions of our program are done. So these 4 instructions are now done, and you can see after this addition, simple addition program has been executed, this result has been produced. So we had this data 20 and 30, and this simple program of 4 instructions was used to add these two values to produce the result 50. And for executing each of these instructions, you see how we followed the instruction execution cycle, where any instruction is executed in a series of steps, and this series of steps is followed again and again for all the instructions. So this is how the instruction execution cycle works and how the CPU functions, how it executes instruction. So basically you saw there are instructions and data in a program, and by executing the instructions, these data are manipulated, and the core idea behind execution of instructions is the instruction execution cycle. So this is how the CPU works. So now that we have understood how does the CPU function, let us now talk about a very important concept that is related to the CPU, that is called instruction set architecture. So basically this is the CPU. We have understood that the CPU, the fundamental job of the CPU is to execute instructions, right? So now basically the instruction set architecture talks about what are the set of instructions that it can execute. So let us understand this with an example. So the set of instructions that a CPU can execute is known as its instruction set architecture, or ISA. And there are different types of instructions that CPUs can execute. So here I have taken a hypothetical example. Let's take a CPU, and these are the set of instructions that it can execute. So this total set of instruction makes up the instruction set architecture, and it is very important because it defines the capability of the CPU, what it can do and what it cannot, right? So if there is an instruction that is present in the instruction set architecture, then the CPU has the capability to execute that. And if there are instructions that are not part of the ISA, then the CPU will not be able to execute those instructions. So let us go over some of the instruction and understand what are the different kinds of instructions that we generally have. So I have divided these instructions into 4 different categories. The first one is load and store. The load and store we have already seen. These are data movement instructions. They are responsible for moving the data between the memory and the registers. So you can see load and store. So load moves the data from the memory to the register, and the store moves the data in the reverse direction, that is from registers to memory. Then we have a set of arithmetic and logic operations. So these are operations which basically perform some kind of arithmetic operation. Here some operands are combined to form a new result. Some common examples are addition, subtraction, shifting, right? In shifting, you have to shift the register by certain bits, and some logic operation, not and XOR. So these are just hypothetical example, just to give you a basic idea. So now let us talk about the control flow instructions. So till now we have assumed that when instructions are executed, that always happen in a sequence, but that is not always the case. So there are times when the flow of control changes in an arbitrary manner. So for example, consider the case of functions or branching or looping iterations, right? So when you're executing a function with, let's take the example of a function call. So when you make a function call, the control jumps to an arbitrary location. And similarly, when you return from the function, the return happens to the instruction that follows the function call. And if you see, while making the function call as well as when you're returning, the sequential flow is not maintained. It's a arbitrary jump, right? Similarly, if you talk about iterations, looping iterations like for, while, do, while. So in these iterations, every time the you hit the end of the iteration, the control jumps to the starting of the loop, right? Again, when you're jumping, the sequential flow does not remain. And finally, let's talk about the branching instructions of if and else. So when you're executing if and else instructions, the flow goes like, if this happens, then code jumps to a particular location, otherwise it jumps to another location. So whenever there is a jumping, right, if there is not jumping, then the sequential flow is definitely maintained. But whenever there is a jump, and jump can happen when you're making a function call, or there is a looping iteration, or there is a branching instruction, in these cases the control flow is not maintained, right? So these are some of the instructions that help us to change the flow of control. So you can see jump 200. So this this instruction will help to jump to a particular location, a particular address. In this case, it is 200. Then these branch greater than and branch not equal are some examples, hypothetical examples, which help in branching. So depending on a condition, whether a condition is true or false, you can jump to a particular location. So these instructions help during branching. Then call and return are used in function calls. So whenever a function call is made, then the call instruction is executed. That helps to jump to the starting of the function given the address. And when you execute the return instruction, then the control returns to the calling function. So this is how there are a set of instructions in the instruction set architecture that helps to change the control flow of the program. Finally, let's talk about some special instructions. So apart from these basic instructions, load and store, arithmetic and logic, and control flow, there are certain instructions that are used for special purposes. So I have just listed a few examples just to give you an idea. So the trap instruction is executed whenever certain error or exception has happened in the system, and the code that is executing, the control has to be transferred to the operating system to take some preventive action. So in these cases, the trap instruction is used. Similar to trap instruction, there is this interrupt instruction. Whenever the program that is executing wants some service or wants the operating system to fulfill some request, then it issues an interrupt to the operating system. So this interrupt instruction is helpful there. Finally, there is this no op instruction. So as the name says, the no op instruction does not do anything. It's a no operation, but nonetheless, it is sometimes inserted at some places by the compiler for special purposes. Finally, there is this halt instruction. So when this instruction is executed, the program halts and the execution stops. So these are some of the instructions that are used for doing special purposes, right? So as you can see, there are different types of instructions, different classes of instructions. There could be other types of instructions as well, but you get a basic idea. So these are the this is how the instruction set architecture looks like. It's a collection of instructions that a particular CPU can execute. So now let us see some more points about the instruction set architecture or the ISA. The next point about the ISA is that it is like a contract between the software and the hardware. So we have said that the ISA is like it's a collection of instructions that a CPU can execute. So the CPU is basically, as you can see in this picture, this is the example ISA that we saw in the previous diagram. So the CPU is basically advertising to the software that these are the set of instructions I can execute. If you want to, basically the software, whoever is writing the software, if they write a program that contains instructions that are part of the ISA, then the CPU can execute that program. So this is how it works. This is the CPU hardware, this is the hardware interface, and any piece of software that will run on the CPU, it has to follow this ISA. It should only include those instructions or operations that the particular CPU can support, right? So this is how the ISA acts as a contract between the hardware and the software developer. And if the software that has to be executed on the particular CPU does not follow this ISA or has instructions that are part of that are not included in this instruction set architecture, then that particular program will not be able to run. So this is how this contract works. So now let us look at some popular examples of ISAs. So within the industry, the machines that we used, some of the ISAs that are quite popular are ARM, x86, and RISC-V. So ARM is used in Apple products. All Apple products follow this ARM architecture. Then x86 is used by Intel. Intel machines are basically designed on x86. And then we have another popular architecture coming up, that is RISC-V. So basically, the way it works is that if there is a machine that follows a particular architecture, let's say the ARM architecture, and if there is a program that has been written for the ARM architecture, then it will only run on the ARM machine. If you try to execute that particular piece of software on any other architecture, let's say x86, since the instructions are part of the ARM architecture, x86 will not be able to support them. So that piece of software that was written for the particular ISA, that is the ARM ISA, will not be able to run on the x86 machine. So this is how these ISAs act as contracts. So while so first of all, the ISA is defined, and then the CPU is manufactured according to the particular design to support that particular set of instructions. And if a program has been compiled for a particular architecture, then it won't be able to run on any other architecture. So this is how you can think as ISA as the capability of the CPU that it advertises to the software. So the final point that I want to talk related to the CPU is the CPU performance. So as we know, the basic job of the CPU is to execute instructions, and the more the better. So as we know, the modern CPU is capable of executing millions and billions of instructions per second, and the push is always to increase this number. So the more instructions that a CPU can execute, the better it is, the more efficient it is. So now we'll talk about some ideas, some optimizations that are used to increase the CPU performance. Before we talk about CPU performance, there are some terminology that we need to understand. So there are three terms. One is socket, the other is chip, and finally there is a core. So let us understand what are these terms in relation with the CPU. So first of all, there is a socket. So it's a placeholder on the motherboard where you insert the CPU chip, right? It's like a placeholder. The socket is where you insert the chip. Then comes the chip. This is the actual CPU, the whole package. When you buy a CPU, you buy a chip, CPU chip, right? Which will be inserted into the socket. And on that CPU chip, there can be multiple cores. Here I have shown a single core. One core is basically, this is where all the execution circuit and registers that we just saw, all the circuitry that is part of the execution is present. So the core has the core functionality, and you can have multiple such cores. So now let us see how can we first of all increase the performance of the core, and then we'll see how can we use multiple cores to increase the CPU performance. So now we will discuss one of the basic techniques that is used to optimize the performance of the core. So this is the core that we are talking about, where all the execution logic is there. And now we are going to look at one of the fundamental techniques that is used to optimize it. So although there are several optimization techniques that exist, but I am going to discuss only one, that is pipelining, right? Just to give you a basic idea of what are all the things that are done to optimize the core, right? So here, first of all, the concept of pipelining, we take a basic non-pipeline code, right, and discuss how the instruction is executed on such a non-pipeline code. So we talked about the instruction execution cycle and said that there are 5 stages, right, to execute instruction. That is what is shown in this diagram here. Basically, these are all the 5 stages that is required to execute an instruction. So let us now see how an example program execution would look like, right? So let's say there are 4 instructions in the program, and each instruction, to execute any instruction, these 5 stages are required. Let's say in this vanilla non-pipelined CPU, until the first instruction is not completed, the second instruction is not started, right? So this is like on the bottom we have increasing time, and on the on the vertical axis we have increasing time, on horizontal direction we have the different stages. So as you can see, as time progresses, these instructions, different stages are getting executed, and after the first instruction is executed after 5 stages, the second instruction comes into the picture. Here I am assuming that each stage takes the same amount of time, but that need not be the case in real life, right? So after the second instruction is done, third instruction comes into the picture, and then fourth instruction. So if you see, there are 4 instruction and 5 stages, so it takes 20 units of time to execute these 4 instructions on a non-pipelined simple CPU, right? Now let us introduce the concept of pipelining and see how this execution can be further optimized. So in a pipelined processor, what happens is that we do not wait to start the execution of the second instruction. Like since the first instruction is executed in stages, and once the first stage is done, that first this unit, the fetching unit, is kind of empty and not doing any work, right? So what we can do, so let's understand this with an example. So let's say you issued the first instruction, the fetch is done, and after the fetch is done, the first instruction goes into the decode phase. But instead of waiting for the entire instruction to finish, what is done is that the second instruction's fetching begins, right? This unit can basically start work since it is now free. Basically, the first instruction has proceeded to the further stages, so we can now start the execution of the second instruction. Similarly, when the first instruction goes into the third phase, then we can move the second instruction into the second phase and the third instruction into the first phase, right? So you basically, the idea is not to wait till a particular instruction is over for starting the next instruction. If that particular stage is available, then a new instruction is issued. So in this manner, the first instruction proceeds till completion, and in this meanwhile, the other instructions also keep getting executed. So this is how pipelining works. And as you can see, after the first instruction is done, at every time unit we are a new instruction completes. So basically here the number of time units that is required is just 9 time units, which is much less than the 20 time units that was required in the non-pipeline CPU. And this concept of pipelining is quite common and used in the automobile industry, manufacturing, wherever manufacturing is done in industry, there this pipeline concept of pipelining is used. It is actually borrowed from manufacturing only, right? So this is how, by executing multiple instructions at the same time at different stages, we can optimize the performance of the core. So this is one of the techniques, and many more techniques like hyperthreading, superscalar processors exist out there, but you get the rough idea. Now we are going to see how we can till now we discussed the optimization of the core. We'll now see how we can replicate the core and further increase the performance of the CPU, right? So this slide shows you different ideas of how we can achieve more performance by replicating the cores or chips. So let us start the discussion with the single core, single processor. Here we have a single socket, that is why there is a single chip, that's why the name is single processor. And on this processor we have a single core. Now the idea is that these cores and chips are made of semiconductor, and the basic building block of a semiconductor is a transistor. So now as the technology is advancing, you can fit more number of transistors onto the same area of chip, right? So this same functionality, functionality of this core can be implemented using a smaller area, because we can fit the number of transistors that is required to make this core into a smaller area. So as you can see, the core size is getting smaller day by day. So the first idea here is that we can have multiple cores on a chip instead of having a single core, single processor. So you see, here we have a multi-core single processor, and almost all modern processors are multi-core. So here we have 4 cores. These are identical cores. The execution circuit has basically been replicated 4 times. So ideally, theoretically, we can achieve 4 times the performance if we compare this with a single core, single processor. Now, the next idea is that instead of putting more cores onto the chip, we can have multiple chips altogether, right? So on the same motherboard, let's say we have multiple sockets. In this case, there are 2 sockets, and so that is why it is called multi-core multiprocessor. So on multiple sockets, we can fit multiple chips. So here we have 2 sockets, and we can fit 2 chips onto these sockets, and they also have multiple cores. So this is how replication can scale your performance. You can either replicate the cores or also go for replication of the entire chip itself. So this was one of the optimization techniques. So apart from optimizing the core itself, you can achieve more performance by doing replication. So guys, this was it for this video. In this video, we talked about what a CPU does, what are the major components in the CPU, and how does it work, basically the instruction execution cycle. Then we talked about an important concept, that is instruction set architecture, and finally some ideas on how we can optimize the performance of the CPU. So guys, this was it for this video. Thank you very much for watching, and I'll see you in the next video. Thank you.